lot of people like to be mesmerized through video. They may like to witness mesmerizing videos over and over again. Some people like to watch these videos in the fashion of over and over. I personally like to play them back and forth. It was November 3rd, 2015. 2015, a year of achievement in the advancement for human rights in the parts of the world. China scrapped its one-child policy. Same-sex marriage became a right in the U.S. Other technological advances in the United States were taking place too. Needle-free vaccines were invented. Google Translate began translating on-the-spot voice dialogue in real time. Apple Pay just came out. Famous movies 50 Shades of Grey, Star Wars Episode 7, Jurassic World, Fantastic Four, and the Steve Jobs documentary were released. I, however, was in my room finishing the only task that would give validity to my life, something that I saw as my greatest ever, as if I was wearing laboratory gloves and delivering it in a steaming cauldron pot I brought to the world from my very own laboratory. An arrangement of text commands, an object handling so clever. It was in the form of digital media. What I had devised was a new and improved way of presenting a series of frames, a different way to view a video as it cooled from its metaphorical smoke. I pondered its potential names. Backforth video, I thought. Yes, this was the first backforth video, the first media example of its type. The thing that would eventually get called Trigonometric Playback. The first of evolution from the standard way of proceeding through a sequence of frames, kind of like a sibling to the video, soon to come as a distant cousin was boomerang. An app that would arrive into people's hands 2 years later on April 11, 2017. Boomerang played videos backward and forward, but it did not incorporate trigonometry. It came from the desire to see a slow motion breakdown of certain videos in history. I wanted to watch particular very brief moments over and over without having to reset the play button, and I wanted to go further and try to fool myself or others into not being able to tell that it's not actually anything more than just a loop and not really a video. I wanted to blur the lines that which were the ending and the beginning. I wanted to get small amounts of useful video and show them to people in this manner and get them to realize what was happening and to get them to sense the utility of it all. I could go back and forth about 15 to 30 seconds of video frames, estimated 400 to 1,000 single picture frames, as long as memory restrictions permit, and it would run an internal loop within these frames at a dynamic speed and back and forth without having to press a button to restart so that the lines where the clip ends and where the clip begins eventually start to fade. I had to approach endpoints of the loop mathematically like a curve, and there was a way of doing that. If you compare the playhead of the video to a graph and you arrange the frame numbers from left to right, 1 to n number of frames, you would travel on a straight line diagonally forward and upward, particularly if you were using horizontal axis as a meter of time and the vertical axis as a meter of current frame number that we were viewing. If you needed to go up or down, you'd call a sine wave to work for you, like calling a cab, a simple sine program to tie the frames we are viewing to a sine wave itself. Would be a pretty cool idea to try and get this going. Why had no one ever thought of that before? It was so strange to see so much technology in this day and age, but no one had gotten the idea to make videos play at dynamic speeds. I cracked my knuckles and began to get to work. Where to begin? I asked myself. As I started a fresh ActionScript 3 file and then what was known as Flash. I knew that Flash would be the vehicle since I had used it to manipulate the frame head in tutorials when I was younger. The engine was going to have to be a timer that would run every millisecond and catch certain events meant to happen after certain amounts of milliseconds had passed. This was the basic way to run any type of time-operative program that carried a user through courses and actions. Additionally, I needed to start seeking out a format of digital media to use to import frames, one that Flash can digest. Formats range in file size, program operability, and compatible devices. Luckily, I was able to get by without AVI videos being able to be chopped into small frames in BMP format using a program called virtual.mod. With these pictures all together in a row with the same naming convention, Flash was willing to import them into separate keyframes and sequence all hassle-free for me. That solved the question of how I was going to contain all the footage of frames in virtual memory. The next thing was programming the handling. The question was there coding for the ability to push the frame head back and forth to a sine wave? We needed tons of variables, so I had to start calling them off, naming them. I had to look at examples of code online, the equivalent of research to do. Moving the playhead was a basic principle in Flash. Manipulating frames of real-time video calculate variable speed for entertainment purposes was what to come of it. Basically, think about any famous video that has made its way into history across the internet. Cute animals behavior, slow-mo experiments, professional sports lucky or rare moments, sleight of hand card tricks, smooth fluid dance moves, or whatever it is. You will at some point or another come across a really important moment in a video that means a lot to you. It may only happen just for a split second, and you wished you would have instead could see it for a while, but not in the only way that currently exists. How do you do that? Let me show you. Unraveling the code. Lines 1 through 8 are imports that must exist at the head end of the main stage's code to allow all the rest of the lines in the code to work. Line 1 imports flash.display.movieclip, which is all the packages and details needed for any code relating to movie clip classes to work, so that the pictures can move across the screen. Without this, no functionality of pictures graphics can be displayed or travel across the screen at all. It's additional lines of code that make up the backbone of the ability for the display of graphical images. Line 2 imports code available to make text boxes work regarding all things input to output. Line 3 imports the flash.utils.timer package, and that allows timers to be created and ran in the scene. Line 4 is for timer events. A package allowing me to use timers to have events occur, basically. Line 5 is for flash.events.mouse event, allowing me to have interaction with the user for mouse actions. Line 6 is a package that must be included for any event to happen from any input or any timer. Line 7, fl.motion.color, is needed to manipulate pixel color when intending to draw single pixel graphics, which will be what we will be doing. Line 8 is a line that includes the package that enables us to return a string representation of a specific object. It is like reading a variable in number form and converting it instead to a text character to display in a text box. After including the packages needed for lines of code to be ran on line 9, we start the next phase, declaring variables. You declare a variable by starting out with the word var, and after the name you put its type. Optionally, you put its starting value too. All on the same line. Var, our offset right now, our first variable, is being declared as a number that represents the offset number, or the frames off from the original point we are on. And when I say we are, that's a myriad of beliefs, because we are both treating ourselves as a side-scrolling magnifying lens on a horizontal wall of film, and we are alternatively treating ourselves as a ticking hand on a very finely numbered stopwatch, numbered to the thousandths of a second. A lot of people like to be mesmerized through video. They may like to witness mesmerizing videos over and over again. Some people like to watch these videos in the fashion of an over and over. The millisecond is treated as an event, and every millisecond calls for the possibility for an event to occur. Line 10 var buttons container is expanded boolean equals false is another variable. The variable is a very common tool for a programmer. This is something we need just to keep ourselves from remembering everything or tracking changes. A variable doesn't really do anything. It just says as a say. A variable is there just to stay saying what you said it said last. What its value is. Its principle is to hold the same for you, hold information for you, or be a result of something for you. A variable can be told what it is or find out what it is by itself, as long as you tell it how to figure itself out. Even using answers from other variables to help solve it. Like, I can use a variable in the form of what time something took by tracking the milliseconds time of now and the time of the event happens in the future, and subtracting total milliseconds minus the amount of time passed where the event started. If I begin running a program and I start a timer to run immediately, it's going to start at 0 milliseconds. It would be a good reference point. This is a way I can find the distance at times between anything. So anyways, I need to keep in mind whether they have expanded the buttons container and the variable type boolean. That only keeps two possible values, true or false, is what I use for this variable type. Line 11 is a variable for color array, which is as a variable I needed to store temporarily random generated numbers when random colored bridges are being created. More info will be on that later. An array is a numbered chart in the form of a variable. An example of an array is open bracket 15, 42, 33, 12, close bracket. They don't have to be numbers. Arrays can also be open bracket, number sign 0000FF52, set. hike. All you have to do is point to the element 3 of the array and the value will be hike. Arrays can be added or removed elements on the go, and the whole point is to know the position of the information you'd like, so that you can use the array by accessing it based on its positions of its elements or length. Line 12 is a variable specific to selection 12.
In the graphical representations that lets me spit out an extra dot every
few ticks of the timer. It serves as a counter that ticks up until it gets to the
number 9 and then reset at 0.
Its role is to play as a comparison statement. When the value gets to 2 and 6, it spits out an extra line of code
to spit out another
my dot. Lines 13 and 14 are related to the variable how many bridges we have in the Boolean variable bridge particles on off, and they are related to one of the graphicalization selections that forms ridges of pixels to mimic the upping and downing of the graph.
As you click the button to increase bridges, more and more bridges in between those bridges are created.
The colors of the bridges in between are selected using the random color stored in the color array. There is mathematics involved in determining
the amount of space between each bridge. As you are allowed to increase the amount of bridges, it will decrease the amount of space in between each
bridge. Line 15, var x plus mult constant is a number
that I'm using
to multiply against a number. There will be a side function to pulsate the animation to make the animation more staggered, which could either be more or less realistic than how it was without it, depending on the case. Line 16
defines a variable called rotation variable, and it allows me to let
users change a coefficient which serves as the speed of the spinning effect associated with 4 of the 13 graphicalization settings. Line 17, related to pulsation effect, is about the phase of the sine wave we are currently in,
and line 18
is related to the amount it translates to, so we can add it. Pulsation phase will always be a decimal between -1 and 1, and it's multiplied by the x plus mult constant to get the actual amount of variance to be applied. Phase, in a broader sense, is any one of the point of a long sequence.
Often things need to be broken up into singular
sections so they can be utilized. You label every tiny chunk
as a phase.
A sine wave in general can be described as a phase where it goes up and then a phase where it goes down. And each point within these points is a phase, because our smaller parts of anything make up a greater whole. Line 19, var, is x pulsation supposed to be on. It's a variable that keeps track for us whether the user has the pulsation feature enabled or not. Lines 20 and 21 are variables that represent the very starting coordinates that other pixels are going to sprout from,
which give you the feeling in the graphicalization that the graphicalization is an ever-flowing vault of dots, traveling and
disintegrating as they are surfing in the air
to the movement
of the flow of frames.
The point at which the my dot will be placed will always be at the x origin,
but the y point will be somewhere varying from the origin. The x and y coordinates of the origin, 20, 150, are predetermined. They line up with the coordinates that we want them to start on here on the main stage. That's before we do some math to calculate
the y that reflects the current
frame we're on. The my dot is a ball of code
at the same time as being a ball on the screen.
The my dot function is written separately in a file called mydot.as, an ActionScript 3 text file. And once you create something that you want to replicate and replicate its code, you start calling this a class, or original copy of something that we are going to make replications of. A class is always nothing more than a text file that contains code and is linked to either a movie clip, graphic, or button on the screen. In this case, it's related to a movie clip the size of a tiny circular dot, and it contains code that propels it to go left or right as time progresses. In other words, the main flash file represents the dot where it should be on the origin x and at the right y value, but the essence of movement of the visualization is all a separate chunk of code in the code for my dots. And all of this has nothing to do with the order or duration of frames of video being displayed, our main use for the program. This all has to do with the graphicalization, a side graph with a bouncing worm of dots on the side that reflects the direction of movement of frames. Let's take a break and look at the my.dot class, because it would surely help us
to do so at this moment.
It's basically a file that introduces a bunch of variables, has a main function where it copies all its values off of the ones you passed on to it,
decides what internal function to run depending on what fade mode you passed into it.
Later on down the code, it has what each fade mode does, which basically increases or decreases the x and y in some way, reduces the alpha value by a little bit, and then have a function to dial and disappear. A couple of the special fade modes
are a little more complicated to explain how they process which direction to go.
The elastic one is a constantly changing velocity and
Applies a constantly changing velocity based upon a
formula that takes the velocity and implements a spring constant. A zero one takes the distance between a target and its destination, and it makes it constantly move by half that amount. Other than that, the dot does nothing except exist and be a dot. Now let's return to our main flash flow actions pane.
Line 22.
Our x phase is a number representing our phase, which is what slice of the broken up equation we are imitating. What number of phase? We have chosen to inject
The numbers from x equals
negative 12 to x equals 12 in every equation we have.
but we have not come to terms with how many slices in between that will be.
We don't have to know. All we have to know is how much distance we want in between each slice of x. Once we have decided how much
Distance in between each x we want increasing between the numbers negative 12 and 12 using
the variable number to increment our x phase by,
we can calculate how many phases that'll take by doing the math
to get there, and then counting how many passes we made. Once we know how much, we can start to make actions take place on each step to mark which step we're currently paying attention to, singling out.
We needed a variable named
Our x phase. If each singular slice in the equation is considered one of the x
phases, then a variable Rx phase
will be an indicator of how deep
we are right into that chart of phases.
Line 23. Keep alives is
A number that keeps track of how many keep alives we are wanting to inject,
keep alives
or the amount of additional frames
to hang on to the current frame when we are detecting peaks and troughs in the equation.
results in one to have more of a hung up effect about keep alives.
When you think of a sine wave, it goes up and down. If you were able to calculate the precise moment you were changing directions, frame that you were going to start
Going in the opposite direction, before going in the opposite direction,
you could hang on
to
to
that frame for an extra 1 or 2 moments. It would make
the springy effect have somewhat of a frozen in place feeling at just the right moment, and it would be interesting. Just as you
in 2022, I finally
finished the programming for it. Line 24, our number to increment our x phase by, is a number that will determine the number of chops that it takes to get from negative 12 in our graph to positive 12.
like we keep repeating, we set this number to
Increment our x phase by artificially to be
0.00225.
because through trial and error, this is what I found
The number needed it to be at
in order for the default equation to work well.
since we are dealing with
Different graphs of x that have different curvatures.
in order to
Take advantage of all the
curvatures, we had to treat
each graph as being chopped up into having different lengths of phase lengths.
alternative equations
Take longer to get going.
or get squirrely.
So they require
Longer numbers to increment the x
phase by, whereas the standard sine wave contains a relatively simpler,
therefore requires
smaller numbers to increment the x phase by. The variable number to increment our x phase by to a user is the starting
starting point.
The
User has the option of incrementing or decrementing the
value on the fly. By the way, on the fly means while the program is running. Variables are always being updated as the program is running, whether you or the program itself will change them. Declaring it as a variable
as opposed
to a solid number allows it to be handled and changed. Line 25.
is bad. We should be traveling up Boolean equals true.
And that's an indicator of whether or not we are going forward in the graph function. When we are going forward, x phase is increasing, and when we are done going forward, we turn around and go backward, and x phase is decreasing. Line 26 says total number of x steps is 1,500, and that's going to be the
Amount of steps we
use before we chop the rest and consider it for
disposal.
whatever x phase is increasing by to whatever final amount. The first 1,500 steps
Are what we are going to use to travel forward.
forward and backward with it. Line 27 and 28 are variables that need to be created to
Dynamically determine the point at which it's a good idea
to go from increasing our x phase to decreasing our x phase. We want to start
good time the change to traveling up to be the same number as
the number of x steps to begin with, because what we are going to do is keep changing it to earlier and earlier as we are processing. In other words, the right time to go back to moving forward is not going to be at x phase 0,
scenario, but an x-phase candidate of when the direction of y values changes in direction from the way it was going before, but the earliest and lowest x-phase that this happens.
Which means that we're going to consider the very last x value
as a starting candidate, and as each moment that the y value changes directions, the earliest change in polarity that is calculated is the value that will be the good time to change to traveling up.
The reason why you want to find a good point of the graph that is consistently changing directions to start going to the opposite direction is because doing it at a moment where there is a change in direction will cause it to happen in a manner that can't be noticed.
And that's good. It's really hard to explain, but a good moment to go up would be at the point where there is a change in the y direction. That is the earliest known change. Line 29 introduces
a variable named total frames in clip, and Adobe is going to directly measure the amount of frames we inject and deliver it to us in number form. A frame is a single travelable moment,
and the longer the clip, the higher the number. It's going to serve as a base for our calculations, which tailor to how long or short the
first looping sine loop is. Line 30 is var suggested amplitude coef,
which is going to be the number we automatically assume is the best number to multiply our y value by to get the ideal range of steps. We want to have a small amount of steps starting out when opening a video file where there is a very small video itself,
and the largest amount of steps starting out when there is a video file with large spans of video.
Line 31 is for a variable called keep alive ticker, which records the amounts of moments where the y value changes from ascending to descending or vice versa.
Lines 32 through 42 are preset determinations that I calculated through trial and error that set the
variable suggested amplitude
coefficient. They start out with an if statement containing the possible ranges 0
frames in clip to 45 frames in clip, and sets the suggested amplitude coefficient to be 0.58 if it's in this case. That would mean that a short video
has a small amplitude to multiply it by the result of y, causing a short amount of frames running back and forth in its
current loop when you start the program. Current loop is where you are in your greater sense of the clip you are having the loop in.
There will be an amount of frames that you are dabbling in, and that will be only a fraction of the total frames.
You can then shift the amount you're working with
as much as you like, forward or backward, until the clip doesn't have any more frames at the beginning or the end.
If your loop that you're working with is larger than the amount of frames, your video is going to become momentarily still
at either of the two ends for a moment, while the y value is trailing far past the number of frames we have.
It works out quite well and does not cause the program to crash, so it's exactly as one would desire. Line 44 says our
delay right now is going to be a number equal to 25.
We have to define a starting speed at which our
animation can run out.
By speed, I mean that there is a timer serving as the engine the program runs on, because the actions of code have to reference time references made by the timer.
And they must happen only on a tick of the
timer. You can consider that lines of code may be ran on any of the ticks of the
timer,
as long as you set how much time it takes to tick the timer in milliseconds.
How fast a tick takes place according to this line of code is 25 milliseconds a time. Line 46 says our amplitude coefficient right now is equal to
the suggested amplitude coefficient. Line 47 says our starting formula choice is going to be
D. Formula choice D is the closest thing to the basic sine graph. When people come to use this looping program, this is the default style that they're going to see to watch the video move back and forth
smoothly and consistently. There are other graphs, like I said,
and I picked them out for their different shapes. There's this one that makes it go forward a little bit, backward a little less, forward a little, backward a lot, then forward again, and it's absolutely awesome. It has the effect of whatever subject it is experiencing uncertainty, wavering
between two choices, and then pausing at the middle. It would then reverse itself in the exact same fashion.
Line 48 creates a new number, but doesn't say what it is just yet.
It just says that this will be the
frame that our computations say we should play. The frame number is useful because of the go to and stop command in Adobe
to tell Adobe to immediately play that frame of the video.
This is a null value so far, different from 0. A 0 is a 0, a null is an empty response. Line 49 introduces an array of
y values,
which is a
big chart that we need to hold the outcome number numbers of each slice of x.
Line 50, finish programming, is a
Variable
variable
that lets us keep track of
Whether or not internally we have finished
running the lines of code that
it takes to generate the array of y values, the table that every millisecond we are going to make comparisons to and change our current frame.
restart. Line 51 is a variable that is
Related to a lock that was originally put on these files that had the whole thing scroll up and lock up after 5 seconds.
If I wanted a file to be locked, all I had to do was go in and edit this
Line
line.
to be true so that the coding later on would occur to lock it up. Having a variable that served as a handle like this to true or false
was easier because it meant I didn't have to go in and
edit out multiple lines of code
For a locked version. Now, in hindsight,
I had absolutely no
success with showing this to anyone,
and it did not go at all
how I thought it would go.
none of this was popular at all.
I could barely show it to anybody. Eventually I decided that it was embarrassing to try to
get
get
people to look at
and pay for something that only I truly cared about. So I edited them out into comments and left them there for history's sake. Line 52, current my dot time to live is the amount of ticks that the my dots of the visualization are going to stay bright for. Line 53, var time to live
timer is a timer variable and fires off the coding to shrink
away and disappear after a
Certain amount of seconds. Line 54 is a line of code that gives a timer time to live timer.
a program to run every time it reaches its amount of time post. Like I said, it's comparable to a
tick of a clock.
The amount of time in between 0 and any length of time can be waited until an action can occur.
This function is played every time
It reaches that length of time set and does a lap.
Line 57 through 60 were lines of code
That I would edit to turn on or off the lock. These lines are omitted from running in the
final versions.
line
58 says we are setting the variable
is file unlocked to false.
On line 59,
The timer would be started and ticks would start generating. Line 64, make the array. Open close parentheses, calls the function make the array.
if we scroll down to line
1411, we have the function make the array where we have the code of the function.
the first line on 1411 makes the name and the header of the function, which has to be there. Line 1413 starts with an if statement that asks if the variable finished programming has the value of false, which in our code is a restricted line of code associated with the task of making sure to make the array function.
Has only run once.
If the condition passes, it will then
Run code, and at the end we'll set finished program equals true, so it
Doesn't happen
over and over again. Line 1415 resets the variable a good time to change to traveling up back to its reset point.
the total number of x steps, and it will
shrink down to its earliest possible result. Line 1416 changes a good time to change to traveling down back to 0.
So it can shrink upwards to its latest possible point.
the latest point where y values change directions. Line
1417 sets the variable keep alive ticker
To be 0. Keep alive ticker goes off each time there is an event called an it didn't just
happen equals false event.
where y values that are in a pattern of staying the same or increasing suddenly decrease, or in a pattern of staying the same.
Same or decreasing suddenly increase. Every time that this variable goes false, which is a moment when there is a last change and a second to last change that are not in the same polarity
as one another. The ticker
increases by 1. If you were to be fed numbers that waver
up and down, but started
going in the opposite way that they were going, after a while you wanted to catch the moments they were starting to go in the
Opposite direction.
You could figure that moment out exactly
by asking at each time the number is read whether the last different number was less than the current number in combination with whether the last different number was more than the last different number. So if I have 3 and 3 again, and then 5, and then 5 again, and then 8, that 8 would not be a moment. But if I suddenly said 5 after saying 8, that would be a moment because you went and increased from 5 to get to 8.
8 and then you decreased from 8 to get to 5.
Similarly, if I was
Telling you 3, 2, 2, 1, 1,
2,
The moment of last different would be the 1. The last different
would be 2, and the 2 decreases to get to
1, and 1 increases to get to 2 to get a moment.
We need to go to line 1493 to show how we are doing this in the code.
On line 1493,
We have just ended up with our temp
Underscore y, our variable that currently
expresses what frame they want to be on.
So on line 1495, it just started ticker is
greater than or equal to 2, meaning for us that a ticker that
counts
How many times this
code
has gone off has only said it has already gone off twice.
and that is because the code outside of the bracket has to run 2 times
before the following code is run.
Let's see what has run outside of this bracket.
On line 1520, 1421, we have a just started ticker plus plus.
This means this runs and increases itself by 1. On line 1523, array of y values dot push is
Us pushing the results into a log.
line 1524, last results y becomes last
Results y.
Line 1525, if last results y is not equal to temp y,
Then last change before that
Becomes last
note is changed, and last note is changed becomes temp y.
finally last results y becomes temp y.
That's what I wanted to observe.
This process of updating a ticker, analyzing your number,
Asking if your number is not equal to the last number,
If it is, shifting it
into a variable, shifting the old contents of that into a different variable.
first, and repeating for every single one of our x phases that produces a temp underscore y.
why we use temp underscore y.
Was to mean temporary y. It was temporary because it was influenced by so many multipliers and coefficients. On line 1499,
We get back inside the instructions to run it.
the last number is different from this number. Temp y exclamation point equals last results y.
And we say, if the temporary y is greater than last results y, and at the same time, the last
Notice change is less than the last change
before that, set the variable it didn't just happen to be false. This is how we flag down a moment. Right beneath that is a similar line. Else, if the temporary y is less than last results y, and at the same
time last notice change is greater than
last change before that,
then make it didn't just happen equals false.
that's if you were going up in numbers and suddenly you encountered down. Immediately after that is an if statement that asks if it's true or not. If it didn't just happen equals false. This code creates keep alive
At this moment,
So we're going to get the best time to go back to traveling down or
traveling up in an x phase number, and it's going to be at one of these moments. Each time it happens, increase the
keep alive ticker.
just to remind you of our two tickers,
Just
started ticker, variable that runs every time an x phase is observed, calculated, and spat into the array.
its number indicates what x phase we are on. Keep alive ticker.
Number of times in the array that the graph changes direction. Back to line 1418. We have a
A few introductions
of more variables
created in this function. Number of variables, last results y, last results y, just started.
ticker, last notice change, and last change before that.
Also, we introduced the
Boolean variable. Are we decreasing or not?
And it didn't just happen.
On line 1425, we
Force dump the contents
Of an array, variable,
array of y values, which will store all the coordinates of the frames. On line
1427 starts a for loop which will run repetitively.
the code within its brackets below
below it until the condition
and its constructor is met
It basically says for every increment
between negative 12 and 12,
or the increment we're using is a variable number to increment our x phase by.
run the code below. Line 1429 says, first make a new variable for
a temporary
y
y
value,
Line 1430 starts a switch/case statement.
which is a way of coding that lets you program big forks in a road. The switch line of code, where it says
Switch is the variable to be
considered, it is paired with the
case keyword, and
together you can tell a program what to do depending on what the
variable is, using the word case to precede each
each case that the variable could possibly be. In line 1432, with case A, where the value of our formula choice reads as the string character lowercase a, it
means the preceding lines of
code 1433 through 1435
are going to run, and then the code distinguishing that case will stop. The word break must come at the end of every case in order for it to run and have no errors occur.
Line 1433 says the variable
Temp y is going to be fed an equation to be.
finally given its contents.
We want the variable to be fed the results of
cosine of i divided by 3 times the cosine of I squared for each time I is incremented starting from negative 12 and
Ending at positive 12, using the variable number to increment our x phase by as the incrementer.
Then, in the line 1434, we wanted to
round to the nearest whole number using mouth.round function, a built-in function.
function into
To Adobe, but
Not only are we going to find the whole number of the temp y we just calculated,
But we are going to first multiply it by the number of frames in our graph divided by
66. This is so we can give these numbers some proper range
before they get popped into the end of the array.
we're building. The plan is to do this again and again over and over until variable I has finally become 12 or greater to come up with an array of y values that is
going to represent our frame positioning.
in line 1436.
36, where we introduce case B.
The lines that follow
Will instead plot the y values to the formula of sine of I plus
the sine of half I, with values being
multiplied by the total amount of frames in the clip divided by 1.75.
in the lines of the formula choice C. The formula choice is
Cosine
Sine of I cubed times the sine of I squared, with the values are multiplied are the amount of frames
in the clip divided by 2. In the formula
Formula D, the formula used is the cosine of I squared
times the cosine of I squared
with values multiplied by
the amount of frames divided by 2.
Formula E is cosine of I times cosine of I squared times sine of I with the values multiplied by the total of frames divided by 0.86.
Formula F is cosine of I times cosine of I squared times
Cosine of I with the values multiplied by
total frames divided by 2. Formula G is the sine of I times the sine of I
squared
times cosine of I times the sine of I with the values multiplied by
total frames divided by 0.8.
Formula H is the sine of I times the sine of I squared times
Cosine of I times
cosine of I with values multiplied by total frames divided by 0.8.
Formula I is sine of I times sine of I squared times cosine of I times sine of I times sine of I
with the values multiplied by total frames divided by 0.66.
Formula J is cosine of I divided by 3 times sine of I squared with the values multiplied by total frames in clip divided by 0.66. Formula K is sine of I times absolute value of sine of I plus 5 cubed with the values multiplied by the total frames in the clip divided by 250.
Formula L is the
Sine of I squared divided by the
absolute value of the sine of I minus 5 cubed with the values multiplied by
frames in clip divided by 0.32. Formula M is the
sine of I times sine of I squared times cosine of I
with the values multiplied by total frames in clip divided by 0.86.
Formula N is the sine of I divided by I with the values multiplied by total frames in clip divided by 1.25.
Maybe.
Formula O
is the sine of I times the
Or
absolute value
maybe
sine of I with the values multiplied
they
by the total
forgot to
frames in
tip
clip
me a
divided by
few
This
years
ends the
ago.
/class
using the punctuation and
Okay,
and no
good.
matter what the case is, the
I
next
want to
line
get to know
code
each of
going
you
to be
personally.
regardless, sets
Therefore, I'm
these
inviting you to my
lines
office.
bracket.
One at a time.
in the code, a calculation is made.
We got them earlier. We would like to allow it to get influenced by the variable r amplitude coefficient right now.
The result of that
Number will be rounded to a whole number. Useful because our
Yes.
animation has
Frame numbers
only accessible
as whole numbers. The higher
May
the
I come in?
amplitude coefficient
Come in.
right now, they are able to
broader range of frames.
I hope I'm not going to receive any more
lets you steep
brutality.
the waves of the graph by adding a coefficient to whatever temp y comes out to be
I'm
each
Bob.
time.
I know.
Next line on line 14
Do you?
is an if statement and compares
You-
the value of variable
Keep up the
just
good work
to the number
and keep your
If it's
backward
greater
views
than or
to
equal
yourself.
Meaning this variable
Yes, sir.
has incremented at least twice
That's
and
it, you
run the
can go.
following code. The code needs to happen
after the incrementing is happened.
twice because it needs the last value and the last
last value before that to start tracking change of direction. Tracking
Change in direction.
is notable.
Chuck, have you figured it out yet?
the main
Are you
feature
sure?
of frames that
That are held still.
Yes, I'm absolutely sure.
In place.
You've got to decide who stays and who
Let's talk
goes.
about that.
after
It's
we
up to you.
move past it just on temporary
No.
These two.
Thank you for your trust.
Ask on line
1497
Thank you.
is
Are the results of temp y the same as the last result of temp underscore y?
because
they are the same. There was no change in temp underscore y.
you need to run this code multiple times until there are changes in temp underscore y twice.
Yes, Mr. Knowles, thank you for your trust. And I was still smiling and dancing in front of that king of Wakanda.
Now you start.
Hey, what's your problem, dude? He's a normal guy with a good sense of humor.
To inject the
Keep alive.
Yeah, we will see how he laughs when he kicks us out.
Keep alive.
Why would he?
Positive 12.
positive 12 is the excellent.
Ask him, Nicola.
Change directions back to the decreasing value.
The earliest moment of interrupted direction, the one closest
Do you really say that?
On the other hand,
Literally.
is the point at which we will change direction.
backwards to forward.
Do you really want to downsize?
Intention of dynamically
What else could
aligning
it be?
the X value.
Maybe he will replace us with his friends from the hood. I don't know. Do whatever you want, but this T'Challa won't fire me. Now it's good.
So the way you stay out, keep alive as you are traversing the graph is by the following.
Hey guys, just a reminder about tomorrow. It's a big day, really important day. It's my wife Nancy's birthday. It's gonna be a packed house, lots of people, a little bit of extra work for you, but I think it's gonna be worth it.
Any special request?
Chef, yeah, she loves your salmon tartare. 3 times yesterday she mentioned it, so if you wouldn't mind putting it together, that'd be amazing.
No problem.
Great, thanks.
A temporary y value is less than
She's allergic to peanuts, so please just be mindful of that.
Are we gonna make the best sound?
If it didn't just happen to false.
Here as well. Both of these lines cause it didn't just happen to be false,
which is a way to notify
ourselves that there was a change in direction of y values. This line of code is going to run hundreds, if not thousands of
times, and for the very select few times that it didn't just happen as equally
false, we needed to run the following lines of code,
which is done on line 1501.
Line
1503. For every number increase from 0 to total number of keep alive,
repeat the lines of code in these blocks. Line 1505, push the last results of y
into the array. That's going to repeat the amount of times that number of keep alives is
equal to, causing a pause right in the very moment that the
animation is changing
direction. To pause for a duration equal to the value this number has.
The end bracket of this for loop is on line 1506, bringing back to the instructions that are running under the if statement. If it didn't just happen,
equals false. On line 1507, there is an
if statement that if just started ticker is less than or equal to total number of x steps, and
just started ticker is greater than the
variable, a good time to change to traveling down. On line 1509, we set the variable
a good time to change to traveling
down to equal the value that's of just
started ticker.
What this line of code asks is for all three of these conditions to be true.
For the fact that we're trying to go right ways,
looking for the most
latest time to go left ways, that the just started ticker we are at now
does not go beyond the limit of x steps, and the current
it didn't just happen equals false moment
we have is later than the one we have saved so far. If all of these conditions are true, we command it
to update the best time to change to the decreasing x values to be as late as it can, so that the viewer
gets the most curvature out of their total range of y values
for the equation they choose. We increase keep alive ticker by 1.
On line 1512, we ask if just started ticker is currently less
than a good time to change to traveling up,
and if so, on line 1514, set
a good time to change to traveling up
to be just started ticker. This is our earliest
it didn't just happen equals false event,
which is the
earliest time the graph changes in
polarity, using the comparison of its last noticed change and its last change before that.
This should be the best moment to change directions in the graph, to going forward, to eliminate seams to the visible eye.
At the end of setting an it didn't just happen
equals false moment,
we don't want what happens to happen again until the next it didn't
just happen equals false moment,
so that every single x
increment doesn't get keep alives added,
and the keep alive ticker doesn't increase like crazy. So we have to turn the it didn't just happen variable to true, so it can be triggered again
instead. It didn't just happen
is set to true on line 1517,
just outside of the calculations for
finding the right time to change to traveling up,
but within the brackets of code for it didn't just happen equals false. On line 1518,
we close the bracket of the if statement of it didn't just happen equals false on line 1519 of the one for the if statement if temp y is not equals to the last results y, and on line 1520 of the one for the if statement of
just started ticker greater than or equal to 2.
Bring us back to the remaining code for the for loop of I being in between negative 12 and
positive 12. It's simple program right here and now on line 1521 to increment just started ticker by 1.
We do that with the
line just started ticker plus plus. It's also important on line 1523
to put the value of temp y into the array.
On line 1524, we have to change the last
results
y to last results y
to keep updating what was the last results y to consistently check for changes.
On line 1525,
we have to add an if statement to say if the last results y is not equal to the temporary y,
then update the value of last change before that.
And last notice
change by making the last change before that become the value of last notice change, and making the last notice change become the value of temp y. Both of these lines of code are on line 1525, one after another, separated by a semicolon.
And very necessary is
the statement last results y equals temp y on line 1526, because this is the time we should be flushing the last results y variable
and replacing it with temp y. We put a closing bracket related for the
for loop of I between negative 12 and 12, and return to the lines of code relating to the if statement of if finished programming equals false.
On line 1528,
we put the line finished programming equals true,
and on lines 1529 and 1530, we close the brackets for the if finished programming equals false, and we close the bracket for the make the array function.
And we're done making the array.
This ends the amount of code that is going
to be run every time we need to recreate
the array of y values. Some examples of
needing to recreate
the array of y values are
after speed modification, amplitude modification, or equation selection. Let's scroll back up to where we left off right after the command make the array open close parentheses. On line 65,
there is a line set children index on open parentheses
zoom nester, comma 3 close parentheses. What this does is it makes zoom nester, the box that shows our picture, come to the front of the display list, third place in line line behind all our preview graphics and data and stuff. If you think about everything as a little paper cutlets glued on top of one another, each object is competing for visual space, occupying the screen. In order to judge who or what should come forward the most, there is something called the display list, and it's ordered. For every object in the display object container on the stage, there is a corresponding element in the display list. Depending on how far up or down the object is on the display list, it's going to be further or closer to the surface of the screen in stacking order. Also, the stage is always
element 0 on the display list in every file, as it is the core element and has no visual display and is a blank display object container.
Also, what is called an instance of the main class of a file is element 1 of the display list, so really, the most buried underneath object that is a visual element in every file is going to be at position 3 always. Zoom master should be third in place from front to back using the setChildIndex command.
On line 67, we
Call a variable into play selection of my dot. It's a number necessary to track the
graphicalization setting
we have. In number 4,
on line 69,
we create
a variable called a timer variable.
This variable will operate like a stopwatch and pull every time the stopwatch does a lap. And this happening is also called a tick.
The timer class is used as the variable type, and for the amount of
milliseconds delay in between, rather than using a number, we will instead replace that with a variable we previously defined called our delay right now. Doing so will allow us to give
the user control over the speed in between ticks, which will give them an overall handle on the speed of the animation. The next thing to do on
line 70 is to attach a function to run
using the addEventListener command to cause something to happen periodically. Line 71 starts the timer. Line 73 through
82 do some zeroing. The container that gives users a
to rotate the animations
gets set back to perfectly straight. The X and
Y coordinates that the animation normally lies on when they are instantiated are restored to their defaults.
The X and Y scale of the SuperNester,
the container solely designed for stretching
horizontally or vertically,
gets set back to a value of 1. The scale X
and scale Y of
Zoom Nester, the container solely designed to grow larger when you click the animation,
returns back to its original size. The alignment within that container that we
off-shift to center the location of our zoom
is also reset to its original coordinate. We do that by doing a little shortcut, combining 2 lines
into one and just doing zoomnester.x equals zoomnester.y equals 0.
Next, on line 84, we found a random place to stick this function definition. The function toggle
is everything, which lets the whole entire display disappear except
the animation. The function begins with a for loop on line 86,
cleverly grasping each object altogether on the screen by the fact that each object is a display object and handling each object as a display object type. It uses the getChildF function to achieve its job
by highlighting each one without knowing how
many there are
or which one it is and applying a comparison to it.
The for loop uses the dummy variable I and uses the condition I less than numChildren,
and numChildren is a property that always equals
the amount of objects in the display object container. By creating a variable called tempChild for every object in the display area using getChildAdd,
we can test this name to rule out that it's not the
container displaying the animation or the container for all the graphicalization buttons. We can then use the
tempChild.visible is not equals operator, tempChild.visible command to work as a toggle switch, making the visibility of each display object
the opposite of what it was, shortening code. So with the not equal operator like that, with an exclamation point before an equal sign,
you are able to cut a few lines
of code down, like 2 if
lines and 2 then lines, just by doing it in that sort of way.
On line 92, we put the closing bracket for the if statement about the name of the child. On line 93, we put the closing bracket about the for loop for all the number of children in the display list on the stage. And on line 94, we put the closing bracket
for the function toggle is everything. And after that, we have returned to the stage code.
We started off pasting things like graph images that clutter the workspace while being in the visible equals true position.
And for that, we would like them hidden so they can only be visible with a rollover of the mouse to initially
hide them all. Lines 96 through 110 contain
.visible equals false commands, which do exactly that. The container they are all stored in is called graphs,
and each image is appropriately named a button letter preview. We also need to code the functions that hide and reveal the preview picture for each equation. Each button that corresponds with each graph preview when rolled over has a mouse forward function for when the mouse is on top of the button, and a mouse out function for when the mouse leaves the button. Note that these are not related to clicking.
They are just related to hovering
over the buttons. Lines 111 through 140 are pairs of mouse over and mouse out functions that are added using the addEventListener command, which listens
for mouse clicks
clicks. They get tied to the buttons themselves.
Each function is appropriately named. We can discuss what each function does briefly if we scroll to line
179, where we encounter our first one.
As you can see,
It starts with the function name, which is
appropriately named as per all our function names. Button
a mouse over function. And the header is like this,
indicating it's expecting a mouse button.
in the body
of each function,
there is a simple visibility command like we've already seen before, tied to a graphic called button.
letter preview.
Each photo
Preview for each graph has a different color palette and the equation and text above the graphic to make it colorful.
Presentable. Line 269 is the last line.
Related to coding hover over and hover out functions.
When we go back to
Where we left off
on line
141,
there are a line of alphabet letter mouse children equals false statements.
The reason these have to be added is
Because these buttons have a text box inside of them. They are
square boxes with text fields inside which have a little information about the button.
I first dragged from one corner to another to create a square. Then I dragged from one corner to another to
Create a text box, and then I put the text box inside the button. The problem with
That is when you're telling Flash the code to receive from the button.
the text inside the button becomes the only clickable part that's going to react.
Since that isn't what we want,
we have to add this command so that any
part of the button, the spatial part, or any of the part that text inside it responds to the click. At least I don't need to do this for buttons where I drew in the text by hand. The last line relating to setting mouse children properties to false for the letter button preview images is on line 155. Line 156
is an added and listener
command necessary to add a function to increase rotational speed.
when a user clicks the button BTN.
What? It attaches the
Function inklot speed, which follows on line 1031. It reads, if rotation variable is less than 50, which is a maximum value limiter, then increase the rotation speed by 1 point. Right below it, line 1036 is the function that does the reverse and causes a deduction of
one value from the rotational value.
But causes nothing to happen if the
rotation variable is already 0 when we click it. Line 158
is a line of code that adds the BTN
expand trails function to the button expand trails. But it is a button that makes the
graphicalization window
become bigger
and closer to the user.
It has a mouse children false command
underneath on line 159 because a text box was used to write the word expand on it. At the code for this function, you have the header on line 160, the function name BTN expand
trails function, and you have that it is a mouse event because it's going
to respond to a left mouse click.
Inside the function, there are statements to set the rotation
to a value of 90. So it becomes sideways, statements to enlarge the scale x and y to 6 times their original size, and statements to set its coordinates to more closely resemble the center
of the screen after enlarging it. On line
167, the variable button container is expanded becomes a value of true. On line 169,
we add an event listener to listen for a mouse
down click event on the button
back trails.
The button also has a text field in it,
so we add a mouse children to be false command
on line 170 so that the whole button responds to clicks. The function on line
171 for button
compact trails function sets rotation to be
0, causing it to be upright. It places the
graphicalization selections panel in the
top left corner again and
scales it back down to 1,
the way it was originally
in line
174.
It also realigns its x and y properties
and sets a boolean called
buttons container is expanded to be false so that we can internally keep track of whether the panel is expanded or not. On line 272
and 273,
there are
mouse down event listeners
to the buttons BTN ink pulsation and BTN deck pulsation,
tagging the functions ink pulsation func and deck
pulsation func to them respectively. On the following
lines 275 to
278, we define ink pulsation func, which has only one line of code
to increase the variable x pulse multicons by 0.1. The lines of code
279 through 283 are for a function that decreases
x pulse multicon by 0.1. They first make a test against the value of x pulse multicon to see if it's greater than 0.1 so that we don't decrease this number down to 0 and have multiplication.
On line
284, we have the function timer decrease delay, which
targets the main timer engine for displaying the frames.
And first tests to see if the timer's delay value is
at least greater than 5.
If so, then lines 288 through 290 will stop the timer,
decrease it by 5,
and restart the timer. If the delay value is
less than or equal to 5 but greater than 1, lines
294 through 296 will
stop the timer and
decrease it by 1 and restart the timer. Line 299 contains function
timer increase delay. On line 301, there is a
test to see if the timer's delay value is less than or equal to 4.
On line 303, it stops the timer. Line
304 increases the delay by 1 point.
And line 305 restarts
the timer.
On line 307, we use the else command, which conveniently allows us to appeal to the other result
when the timer value is
greater than
4. And on lines 309 through 311, we stop the timer, increase the rate by 5 instead of 1, so that it increases further faster at that point. That means the timer rate can be any of the following selection: 1, 2, 2, 3, 4, 5, 10, 15, 20, 25, 30, and so on.
Because we said if it's less than 4, add 1. If it's greater than 4, add 5. And to reverse, we do the opposite. If it's
Greater than 5, subtract 5. Less than 5, subtract 1. We have a couple of little closing brackets for the else command and for
The function increase delay. On line 315,
we have a function for the mouse click,
click and it contains a pass-through mouse event.
parameter.
So along with the function being called, the line of coding also provides the function facts.
Relating to the mouse click, like what mouse button was used.
The function has no other purpose but to call another function,
Function timer
increase delay, that asks if the timer delay value is greater than
5.
It tells it to
Subtract 5.
Or if it is 4 or less, it tells it to subtract 1.
The function below on line 317 calls the other function saying timer increase delay, open and close parentheses. On line
319, we have the line of code that ties the function to the button that's clicked to cause this function to happen. Button BT and timer decrease
Delay. We have mouse event, which
needs to be there always, and mouse down, meaning we want this to happen as
the user clicks on the button.
on line
320, we have the same line of code that calls the increase delay function by clicking the button.
BT and timer
increase delay.
On line 322, we have a mouse children false command
for the X pulsation button.
And that lets us click any part of the button, including the text.
To activate the button.
Line
323, we have an added
And listener command.
to listen
for a mouse click on the button.
BT and X pulsation
Which causes function
Toggle pulsation.
function to run if it is clicked. On line 325, we have function toggle pulsation.
Function which in its
Function body conveniently asks without an if statement for the variable is X pulsation supposed to be on to be equal to whatever it was not equal to, something which only works with
Boolean variables.
the on/off
variables. That's like saying in
computer terms on line 327. It means
make me now the opposite of
what I am.
on line 330, function tint color is a function
which will accept the variables into it as it's being called, a variable of type
movie clip,
MC, that'll be whatever object we pass through this color num,
which will be a color number.
representing the hexadecimal value in hue, and alpha set, a decimal related to transparency. The first line starts a variable of called ctint and makes it a blank new variable of type color object. Then it uses the simtint command, which is a pre-stored library function available to use on any type of movie clip. It uses two parameters, color number and alpha set, which we provide by passing through straight from the function calling. Then you must use the .transform.color transform command on the movie clip and make it equal to the color variable we just used the set tint command on.
Doing this allows us to change the color of the my dots. On line 336, we hail the main timer function where we have
All the code that is being ran at every single tick of the timer. We have to slow down very hard to be clear at this moment because
this is the function that serves as the engine. It's going to run at every time increment that
Passes during program execution. It's going to do
everything it needs to convert our variables into a frame number that should represent where we should be.
be at in our video.
with dots coming in on the side representing the frame number
In an up-down visualization, the main timer program also changes output labels as it
Updates the variables we need to use to compute this result at every increment. The line 338 begins the function by using an
if statement to ask if the X pulsation is supposed to be on variable.
equals true, and if it is, then it
Makes the visibility of a red box around the contents of the label
to be true,
On line 339, it does the opposite.
making the red frame
disappear if it's false.
The red box informs the user of whether pulsation is activated or not. Lines 340 through 355 update all of the variables being used real time on the right side of the screen. All of the labels are extracted from the variable form by using the string, open parentheses, variable name,
close parentheses command, allowing you to display the variables in a text box.
There is a my dot centered in the display
Object container buttons.
underscore container dot rot container dot group underscore 1.
and on line 356 we set its
Y coordinate using the formula 25 minus SC dot current frame.
Times 100 divided by SC dot total frames.
This is going to make the dot take a position of higher or lower depending on what frame we are on. And since this is just our initialization dot, we wanted to reflect the starting frame. On line 357, we set the alpha of the initialization dot to be a random
Transparency. Alpha values have to contain
exactly one decimal point. So converting a random number between 8 and 10 to a decimal but dividing by 10 is a necessary step
to do. Line 358 creates a new my dot, which is the first dynamically created my dot that we put down.
It's the very basic red dot that gets created in the side graphicalization, no matter which setting you are using. You're going to see it
Available as we scroll through each of the different graphicalization settings. It's the one
red one that is always present. There are 5 parameters that must be passed into
to the my dot creation function, and that is because the coding for the my dot does a lot of moving processing internally.
It only
Requires you to let it know it's time to move whether we
should be traveling up
is true or false.
the
or is an X that
or
origin y and the fade mode parameter.
On line 359
through 361,
we set the new I dots x, y, and transparency values
to be that of the dot
that was put on stage in
Pre-production. The one that
We'll
will
set its y value with an equation of a few lines of code ago.
On line 362, we use the color tint function to
Change the tint of the new my dot to be
red.
red.
On line 364,
where we add the dynamically
Created new
my dot.
the stage in the container buttons, container.rot
container.group 1. We say
that
that we added
to the stage, and what that line on
364 does is it creates
the new dot in the display list, because creating a dot and adding it to the display list
list are two different things. For any object that is created dynamically using variables
And classes,
it takes one piece of code to
make the object.
and another piece of code to put the object into vision.
we have been talking about something called the my dot class.
And then to know what a class means, you have to know
Everything you know about present day,
about the word class that you've ever learned.
And imagine the word
Class is a mold
or cutout of something, like a cookie cutter.
You create lines of code that make up and describe the core essentials of
What makes an object an object? Lines of code to run that run no matter what different variation of the object is.
They may be things you know are going to need to include,
So that every time you call the function to create the object,
it already has the variable names provided for the things that are expected to come along with it.
this could be the flavor of
The date created,
the amount of dollars, the weight, the size.
any and
whatever preset determinations.
you said were going to come along with an object being an object.
The my dot in this case is an object created from a whole separate file, and every time our main file
Means it erases it from the
Separate file. The my dot class looks like this.
Line 9A, public class my dot extends movie clip. A movie clip in Adobe terms is just a fancy word
for a box that can hold an image or sequence of images. Below that are all
preset determinations. A variable called its time to live, a variable called its we should be traveling up, a pair of variables called
Origin x and y, and a variable called fade mode
These are all related
to the dot and its ability to move and change visibility.
visibility
within the graphic.
representation. There is a main function that gets called
When creating a my dot, and this file is ran, which is lines 23A through 27.
7A. The point of these lines of code are to declare all the variables in order to prepare them to get ready to be used. Then later on,
Go
49A, when we have these functions that we have ways this dot is going to
proceed upwards,
ways and die out, down ways and die out.
proceed
in an elastic manner and
die out, or proceed using Zeno's paradox and die out. Zeno's paradox states basically that it's impossible to reach a distance if you just travel half the distance
in a step.
each move making a half step further and further. Zeno's paradox and elastic bounce effect are all features intended to make the graphical representation look
Cooler and have options. For now, we will return to the
main flash file and leave the my dot class B. Line 365 creates one of 5 particles, which are another different class. My dot custom slope. My dot custom slope objects.
Are designed to propel movement in one direction and disintegrate.
They don't have all the other different options like my dots, like traveling with electricity
or traveling using Zeno's paradox.
and they lack the 4 different directions for movement and fade off. These instead
Except their slope given to them in
their calling parameter to propel in that direction and fade out into disappearance. Particles look like
Smaller my dots. Small dots of color running away from one another. The smaller, simpler particle accepts only 2 parameters.
an X
velocity
velocity
and a y velocity using a random
2 command
To find a random x slope and y slope
for each one. We can call the creation of these particles in function.
form and start to treat them like variables. We call them up on lines 365 to 369,
and on lines 370 and 374.
where we call them onto the display list.
Line 375 begins the great deviation of the selection of my dots.
If our my dots
Selection is
0, meaning our way we want to display our graphic.
Visualization is the very first way, with a simple red dot reflecting the current
Y value, then there are no lines of code to be ran for this condition.
Line
379 starts a code for selection of my dot equaling 1,
which is the second selection.
apart from the red dot reflecting the Y values, there's a second
Blue dot
reflecting negative 15
plus current frame times open parentheses 100 divided by
total frames,
close parentheses.
which is on line 383.
This gives a mirroring effect at a certain height in the graphicalization.
Lines 384 through
393 spit out some
My dot custom slopes to make sprinkles come out of my dots. Essentially, line 394 gives
the selection of one dot on blue tint. Line 395 produces the my dot on the
stage for it to take
visual precedence. That's it for selection of my dot equaling
1. Line 398 begins the code of when selection of my dot is valued
2. Our third possible selection, a deeper blue curve that lies closer in translation to the red.
my dot and a y value is what the selection produces.
The way we calculated it on line 402 is negative 12 plus open parentheses current frame times 100
divided by total frame, close parentheses times 2. That times 2 is what gives the wave its doubled amplitude.
from the blue wave produced in the previous selection. Lines 403
through 412
Give it 5 particles that randomly spurt out at random velocities. Line 413 gives the my dot from selection 2 a blue tint. Line 414
adds the dot to the display list. Line 416 begins the code sequence for
My dot selection 3, the fourth selection.
Line 418 calls the variable into play
using the class my dot. We see that it's
variable constructor and the keyword
Zeno is there. That means that upon each tick in the dot,
it will reach half the distance
to its destination
forever until it fades out. The origin x and origin y
parameters being fed in as the my dot is being created are the original my dot's
coordinates minus 25, so it will travel upward
and backward to 25 points as its destination is flowing. This is why it looks like
it's a flying away blue ball that's always going left
no matter whether you're traveling up the graph or down. The lines
421 through 430 give this selection
of my dot particle effects.
Line 431 gives it a blue
color. Line 432 adds it to the stage. Line 434 begins the code for selection of my dot 4, the fifth graphicalization setting, which causes the new
my dot to see
its way toward the mouse cursor.
First, it needs two variables declared as empty variables on 436 and 437. They are variables which location to be x
and which location to be y. If the button's container is expanded on 438, then which
location to be x is
0.17 times mouse y minus 32.
This is how to get the my dot to follow the mouse in the best manner depending on whether
the button's
container is expanded or not. I want to mention that expanding the button's container is synonymous with expanding the graphicalization.
The same thing is calculated for the y coordinate when the button's container, and that's which location to be y equals 0.17 times mouse x plus 130. On line
443, if the button's
container is expanded equals follows,
then we need to use these calculation
methods instead to find the right x and y coordinates to zeno towards. Lines 445 through 446 tell the computer how to calculate that.
Once you have successfully established which location
to be x and which location to
be y, you can move on to creating the my dot specific to the selection.
We created a my dot on line 448 using
which location to be x as its origin x parameter,
and which location to be y
as its origin y parameter, and zeno as the fade mode. It gets 5
sprinkles,
with each sprinkle added to the display list, just like all the previous others.
It's converted to the hex color blue, 0x0000FF.
Visibility value of 1, like all the previous others.
Line 464 for selection of my dot 5, the sixth selection.
Uses a static number 5 as the origin mode, and new my dot
y as the origin
y, and uses the elastic feature embedded within the my dot code.
The elastic feature causes an object to overshoot its distance
on its way to its destination,
causing it to
travel in backwards direction.
It will overshoot its
target again, but a little less forcefully,
and it will spring back in an attempt to get to its distance again, over and over. Each my dot created does this,
and it makes a huge blue mess that, in my opinion,
looks like a waterfall,
and it ended up not
being how it was intended, but it was kept because it wasn't a priority to get it to look good. It's worth mentioning this line is also going to be blue too. Line 482 states what to do if my dot selection is 6.
There will be a blue line mirroring
the red line and a green line split right down the middle. This will take place using the formula on line 486. 39 plus
current frame times open
parentheses 100 divided by total frames. Then on line 501 we take the average distance between the original new my dot and the my dot created for this my dot selection and divide the combined y values by 2. The result is a line of dots that stays exactly in the middle between the other two lines.
There's not much to speak about that.
We haven't already covered, so we will be moving on quickly to the next my dot selection. Line 515 starts the instruction of what to do when selection of my dot is 7. It creates a blue dot calculated by 35 plus the current frame times open parentheses 100 divided by total frames close parentheses times 2 on line 519.
Also a green one, that is the y value
of the new my dot created plus the average between the new my dot's y value and the original y dot's my value on line 534.
So it's going to have a green line that, like the blue line, is a mirror of the red line, but twice as far away.
On line 548, the code for the selection of my dot 8 begins.
The y value is
negative
2 plus the current frame times open parentheses
100
divided by
total frames close parentheses times 1.33 on line 52.
Another my dot is created using an average of the new
my dot's y property
and the original my dot's y property,
which is done on line
567. It's given 5 particles. The particles are called to the display list, and then the my dot is added to the display list. On line 580, the display object container buttons
container.rod container
has its rotation value added 2 times the rotation variable.
The result is the original
red line, a blue mirrored line above the red line's axis,
and a green line split
down the middle,
slowly rotating clockwise. On line 582, the code
for selection of my dot now begins.
This is the selection known as the one with bridges.
It creates a blue dot
using the formula negative 15 plus current frame times open parentheses 100 divided by the total frames
close parentheses.
Then on line 599, it declares a number
variable difference between x and populating it with
the value of new my dot 13.y minus new I dot y. The next variable called integration is the first
How many ever
distance, and that is equal to difference
between max
and min.
Divided by open parentheses,
However many bridges we have plus 1.
close parentheses.
The reason why I do this is because
We need to
divide the amount of space we can
work with by the amount of bridges that we need to
place, so that we end up finding how much space we need to
split for per bridge.
This gets accomplished on line
601 by a for loop created that says
For every time that this letter L is going to increase by 1 until it gets to be no longer less than or equal to the variable how many bridges we have, do the following.
create a new my dot called new my dot dynamic. Make its y property
the original my dot y plus the first of however many distance.
times the current L.
This gives the bridge a nice even spread mathematically, dividing the total amount of free space by the amount needed to divide by. Next, we need to ask if the bridge particles variable equals true.
The reason we decided to give users the ability to turn particle effects on or off for the bridges is because when they are enabled, it causes the computer to draw a lot of dots on the screen, and it can slow
Program down for some. If the variable is in fact true, then we add these 5 simple
particles to each my dot as we are creating them. On line 619, the tint color command is used to apply a color stroke
To the dot created using positioning reference.
L minus 1
as the way to get it in the variable. L for the sake of the form, we're going to start at
1, and our array starts at
Position number 0.
so we have to put minus 1 when
translating L value to color array
Position. Line 620.
adds the dot
to the stage, and that adds the code for the my dot selection.
9. Line 627 for selection of my dot 10
Places a new my dot at the y of -2
plus current frame times open parentheses 100 divided by total frames close parentheses times 1.33.
This creates a mirrored line above the
Axis of the red dot that we change the tint on line 638
to blue. On line 640, we
create another dot,
and on line 642 we place it at the average
between the y coordinate of the original dot and the y coordinate of the newly created dot.
On line 653, we color it green, and on line 654, we add it
To the stage. One thing we also do
during this my dot selection is, because the selection causes the graphic
realization to spin quickly, we subtract 25 times the rotation variable from button container.rot container's rotation property,
which happens
to be on line 655. On line 657,
the coding for the selection of my dot 11 begins. It features a mirror blue line
and a green line splitting between the red line and blue lines,
and its rotation is a mixture of the mouse
placement plus the current frame, making it rotate
very unpredictably. On line 661, the blue dot y placement is
set at -2 plus current frame times open parentheses
100 divided by total frames close parentheses 1.33. On line 676, the green dot y placement is set at the average of the new dot and the original dot's y's. On line
687, we change the color to green, and on line 688, we add it to the stage. Also, some additional
calculations take place below.
On line 690,
if the button's container is expanded, we use these comparisons that follow. The comparisons make the right distance
checks to make it where the mouse is still considered
orbiting the
target, regardless of whether the button's container is expanded or compacted. It starts on line 692 by calling a variable into play, variable cy,
which is going to be equal to the mouse's current y value after having subtracted the new my.18's y value from it. On line 693, it does this
with the variable name cx, with the mouse's x value as well.
On line 695, it creates through the mathematical tangent command
math.atn2 using cy and cx
a variable called radians,
which is the angle in radians of the point that the mouse cursor hits the target object.
We will need that in degrees so that we can apply it to a rotation value
to get an actual use out of it. So
line 697, the variable
radians is converted into variable degrees
by multiplying
times 180 and then dividing by pi. Line 699 then implements this by making the buttons
container.rot container's rotation value equal to 40 minus
degrees plus current frame
times open parentheses 1.1 times rotation variable close parentheses. On line 701, we begin calculations to
run if the button's container is in the compact state
where it's sitting in the top left corner of the screen.
Instead of subtracting new
my.18's coordinates,
this time you subtract button container's coordinates.
Line 703 and 704 say
bar cy2 and cx2 are numbers equal to mouse y and
mouse x properties minus buttons container.y and buttons container.x
respectively.
The difference is that the anchor point
to which you compare your current mouse properties to changes
due to the origin changing from where it is on screen
between the compact version and the expanded versions of the buttons container. I should make note
that the word buttons container is a poor choice
of words for a name
because it is not exactly a container of buttons. No, it's also the entire my dot graphicalization display and all dots
within it.
So every time I say the name buttons
container, I really mean the object container that holds all the elements
elements of the graphic.
Localization, which is the thing going on that's taking place off to the side. Line 706 and 708
Calculate the angle in radians and then
Degrees, just like when buttons
container expanded equals true.
except for now we're doing it when it's false. However,
On line 710, what is different is the rotation property.
as this time it's negative 38 plus degrees plus current frame times open parentheses 1.1 times rotation
Variable close
parentheses,
it's a little useless to talk about these calculations.
because they are
purely senseless.
There is no good reason why we should be using these variables in this manner. It was done just for variety. On line 713,
We have the selection of
my.12 code, which spurts out extra my dots that travel in
Different direction than the usual my dots.
every so often. There will be one new my dot with the same my dot as the original, and another new my dot for negative 15 plus current frame times open parentheses 100 divided by the total frames close parentheses, causing a familiar red and blue
line. On line 746, there is a selection variable allowing us
to count
Up until the variable is equal to 2. And when it is, make a new my dot that is equal to the first new my dot, but with the fade mode
parameter upways instead of none. This makes it where there's a large blue my dot fluttering away up.
ways every time this variable becomes number 2, which according to the fact that on line 818, it increments by 1.
And according to fact on line
819, it resets when it gets to number 9.
back to 0.
every 10 times. Also, the code
Repeats for a large red my dot fluttering away upways
2
2
at the same time on count 2.
On line 782, we have the code that runs when
selection 12 variables.
greater than 4. On line 784,
We see what happens
When selection 12 variable specifically becomes
6. A large my dot flutters from both the position of the red
my dot and the blue dot, like in line
752 and 767, except they are
programmed to flutter downways, and the variable declaration has the corresponding word
downways
in its fade mode parameter to indicate that. That will happen on the 6 count of every 10.
So what you have is a quick
flash of 2
Going up or down the 2 count, and a quick flash of 2 going downward on the 6 count.
The counter ticks up so fast that
it looks like it's happening at the same time.
on line 822 we have the code to run for when the
Selection of my dot is 13. At every tick, 6 different my dots are created. 2 that are going
forward, whether that be the left or right, 2 going forward upward, and 2 going forward
downward. It's like
the previous my dot selection, but with the additional my dots that were happening every 2 and 6 counts instead going off every single count, causing an immense cluster of dots. They have the 3 same y values and are red, and their fade mode is the only thing that differs, meaning that internal coding that governs whether they should travel forward,
downward, or forward up.
Handles them differently from one another.
The other 3 that are blue have the same
My values as one another as well, with their fade mode governing how they move forward as well. Red my dots,
Y values are calculated on lines 856, 871, and 886.
blue
my dots Y values are calculated on lines 826, 841, and 901.
They're all given color by the hex number
Number in the 10th killer command. There are no more selections of my dot values
past 13.
So the closing bracket returns us to the lobby of the code that is run for every
single tick of the timer. The following code on line
916 runs the
variable finished
program equals true.
On line 19, the variable frame R
Computations say
gets defined as
the contents of whatever is in the array of
Y values
at the position number coming from the variable r hex phase. This is considered our frame number before our offset and pulsation additions have an influence on it. On line 921, we calculate the variable x pulsation
to add, which is the variable
that gives us
the value of pulsation amount that should be added.
influencing the results from this tick. The variable is made by taking the rounded off number
The sign of x pulsation phase, the number
in radians, which is multiplied by variable x
plus mole constant, which is something that we have control over.
The line below it says x pulsation phase plus equals 0.25.
which pushes the value of the variable up
Every tick moving
Forward, line 923 says if x
pulsation phase
becomes greater than or equal to 2 times
pi.
then we set the value of x pulsation phase back down to 0. We want
A
to
loop that's going to be continuously adding and subtracting values in a wave.
And what the value of sine 0 to sine 2 times pi is going to do is go exactly
From 0 to positive 1 to negative 1 back to 0 again.
so we
Can add that after multiplying it by a multiplier we have
handle over
so that we can get
somewhat of a pulsation effect.
added to what's already going on. Line 924 is the single line of code that's going to take all of our factors
And put them together and figure out just precisely what
frame we should be
be
on.
on. We have 3 influences on this result,
We have the r phase number.
which is the point at which we are located from left to right.
Our graph,
we have our offset
Right now, which is a number that the user shifts
shifts around.
that allows them to watch sooner or later from the clip. And we have the x
Pulsation to
add, which is a looping value from a negative value
to a positive result. These 3 come all together to tell you the frame
which you should be currently
doing.
and the command to send the viewer to a precise frame.
In Adobe Animate is go to and stop, open parentheses, frame number, close parentheses.
So we have a big formula there in place
Place a frame number
That gets calculated every tick of the timer. I think that's brilliant. Conveniently, there is an else command to run
when exposition is not turned on, so that there is slightly less
load on the PC.
the same formula
minus the addition of exposition to add part
on line
926.
So the first step was to make the array, then the next step was to read from the array at every few milliseconds
Of the clock.
Any changes
That are made by the viewer that are mandatory to the composition of the array will cause the timer to
stop, cause the program to
remake the array after the changes, and then cause the timer to start reading from
the array again. On line 927,
We have a line of code that makes a switch from
traveling backward in the
graph, decreasing x.
to traveling forward in the graph.
increasing x.
It says if we should be traveling up equals false, meaning for us, if we're at a point where we are decreasing one value from our x phase every time, and at the same time, if our x phase is less than or equal to the variable that we have named a good time to change to traveling up, then at this point,
We want to set the variable we should be
traveling
up to be
true. It's almost like saying, have we reached our limit? Yes, so let's
Turn around. There is another line of code on line 928 which calls
for action in a similar case as line 927,
but mirrored to the opposite end. If variable we should be traveling up is true,
meaning
if we are currently increasing
our x phase, and we get to a point where our x phase
is now larger than or equal to
open parentheses keep alive ticker minus 1 close parentheses times number of keep alives plus a good time to
change to traveling down.
minus times number of keep alives.
then let's start turning around. It says,
The keep alive ticker minus 1 times number of keep alives part, because as we inject keep alives to our graph, the best point to change to traveling down gets shifted further and
further with each keep alive frame.
we inject it to the
The array of white values.
We lose the prediction of when it's a good time to change to traveling down with the introduction of the whole keep alives part, but that's okay, because through careful addition,
we found a way to keep the transition from going forth to back seamless again by keeping track of the exact amount of keep alive frames by calculating how many times we
shifted directions, keep alive ticker,
and subtracting
1 because we want to account for the one we are turning around at.
and multiplying that times the
number of frames we keep alive for, it will tell us the exact amount of keep alive frames we are using up,
allowing us to calculate when would be the new actual time to change directions
to traveling down
By factoring in those keep alive frames for
consideration. It's like changing the endpoint of a bookshelf as you keep injecting more and more
books into it, as if
magically
making the shelf longer and longer, but somehow
stretching the wood out basically.
line 929 says,
If we should be traveling up is true, increment the variable our
x phase by
1. Line 930 says else, which would mean if we should be traveling up is
false, then decrement our x phase by 1.
We make note of the
Closing bracket for finished programming equals false.
and make note of the closing bracket for the timer main
function.
This is where we stop the code that's
Going to run
every tick of the timer, and we have covered a lot.
the code
That runs every tick of a timer, refreshes on-screen labels, determines what manners to place line instances in,
places them
and mathematically computes
computes what frame we are supposed to be on using 3
variables.
and then pushes us there. After that,
There is nothing left but functions.
which if you haven't realized by now, are just
Many programs. Line 934 has the function
increase
number of keep alives. It has a mouse event parameter
because it's a function activated by a mouse click. The function increases the amount of keep alives by 1, sets the finished programming variable to false, then remakes the array.
The function on
Line 940 decreases the number of keep alives
after first making a comparison of
the number of keep alives to 0. If it passes the if statement,
which just makes sure it doesn't decrease it past
0 and crash, then it will allow number of keep alives
to decrease by 1. Also, it marks the variable finished programming to false.
It calls upon the
make the array command.
function increase offset amount
x5 on line 949
will do nothing more than change the variable our offset right
now
by 5. Line 953 contains function increase offset
amount, which does the same thing but increments it
by 1. Line 957
Function decrease offset amount will decrease our offset.
right now by 1.
Line 961 has a function that will decrease the offset by 5.
Line 965 increase trail amount standalone will perform the following actions.
Compare current y time
To live to 150. If less than, increase the variable by 1. Otherwise, don't increase it.
By anything.
This limits the max number of my dot time to live to 150. That way you can't accidentally set the dots to stay alive long enough for them to jam up the memory.
Line 972 is another function that responds to a mouse click, but the function's sole purpose is to call another function to save on memory.
Line 976 is a function that decreases the current
Y time
to live
by 1. Line 980 is the function increase trail amount. It calls increase trail amount speed standalone function. I should state why there is a mouse click function and a standalone function for some
The
other
tasks we need to program to do that just
seem identical. Functions that are activated by keyboard presses cannot set off functions written for mouse clicks. And mouse click activated functions cannot set off functions written for
keyboard presses.
For that, you need functions that point to other functions, like a function that is neither keyboard nor mouse activated, that can handle both. Later on in the code,
We will read what keystroke was pressed and go multiple routes depending on what the key code of the keystroke was. If we didn't have standalone function, we would need to copy and paste all the lines that took place in the standalone functions twice.
once in a function for the mouse click and another
During
during
the key press comparisons,
line 984 is a function increase current amplitude. The mouse click function calls for a function increase current amplitude standalone.
After that, on line 877 is function increase current amplitude standalone, which stops the timer, increases the variable hour amplitude coefficient right now by 0.01, sets finished programming to false,
Calls make
the array function,
and then restarts the timer.
These are necessary steps to rebuild
The array
after changing it so that curves are steeper.
below that is
function decrease current amplitude. Its job is to
Receive a mouse click and to call the function
decrease current amplitude
standalone. On line 1000 is function decrease
current amplitude standalone,
which asks if
our amplitude coefficient right now
passes the greater than or equal to
0.02 test.
If it does, we decrease it
by 0.01 for stopping the timer to do so,
and then setting finished programming to false,
making the array and starting the timer again.
On line 1011, we have increase
Current amplitude by 5, which does not need a standalone function because there is no key press to increase amplitude by 5, which means this code does not need to repeat twice anywhere, just once in the mouse click function.
The code stops the timer, increases the
Our amplitude coefficient right now variable by 0.05, sets finished programming to false, makes the array and restarts the timer. On line 1019, we have a decreased current
amplitude for X5 function
Activated by mouse click, which first tests that our amplitude coefficient right now variable
is greater than or equal to 0.06,
then stops the timer, decreases the variable by 0.05,
sets finished programming to false, calls the make the array function, and restarts the timer. We already talked about what
function
rod speed and dec rod speed do. They increase and decrease the rotation
variable. On line 1041, we have
function increase speed function, which is a mouse click function. On line 1043, that function
calls a standalone function to run. On line 1045, the standalone
function first tests to see if the variable
number 2 increment r x
phase by not too large by testing
to see if it's less than 1 minus the amount we plan to increase by. And if it passes, we do the code execution. Stop the timer, increment the variable by 500 thousandths,
set finished programming to false, call to make the array, and restart the timer.
On line 1056, we have the function decrease speed function, a mouse click function that calls decrease speed function standalone to run. On line 1060,
we have the decrease speed function standalone, which tests to see if subtracting the
amount of to subtract by from variable number to increment our x phase by would make it smaller than
the tiniest amount we allow, 0.0005.
It's like
we're saying you only decrease by the amount you want to decrease by
until you reach the amount you want to decrease by, which will be 1
unit away from 0. On line 1065, it's going to decrease the number 2
increment our
x phase
by 500 thousandths or
0.00005. Like all other functions that edit the calculations
made to come up with the array.
We stop the timer, set finished programming to false,
call the make the array function, and restart the timer. On line 1071, we have the function
to increase the speed by 2 times the regular amount. It asks if the
number to increment our x phase by is less than or equal to 1. If so, it adds
2 times 500 thousandths to the number to increment our x phase by. Likewise, on line 1082, we have the function to decrease the current speed times 2 amount. It asks if the current number to increment our x phase by is greater than or equal to 2 times 500 thousandths plus 500 thousandths.
It just makes sure that
there is at least one 500 thousandths away from 0 left after you've subtracted 2.
This is so that if you go into a clicking frenzy and just for experimentation
try to decrease your number to
increment our x phase by down to 0, it doesn't allow you to.
We know that if you decreased it too far, you would never reach the end of building the array. You would repeatedly plug the first
y value you get from the first x phase into the array
over and over and never move along. The processor would waste away processing instructions
endlessly because it waits until the array is done before it resumes
thinking about anything else. That's unfortunately the way threading and microprocessors work. They can stay busy infinitely
with an instruction because they're loyal and faithful machines.
And it's our mistake if we tell them to process things that go on forever.
Now on line 1094, there is a chain of add
event listener commands. Therefore, all
a different formula formula buttons. These add event listener commands
all cause it to where if you click down on a button
To change the equation of a formula, it runs a program to make the change.
each function to change the formula can be found
Later on in the programming, at line 1290,
You can see that on line 1290. There is the function name.
2 lines after that, it says the our formula choice line that designates what code letter it is being assigned to. It sets the
Finished programming variable to false, sets the number of
keep alive variable
to 0, sets the number to increment our x phase by,
to a number that suits the equation well.
and runs a function called
called timer.
Reset function.
It does the same thing for each formula choice,
changing the string letter of the variable for each different
our
Formula choice
the point at which this character letter comes into play
is when we are making the array. Recall that on line 1430, there is a switch command and the
variable observed
is our
formula choice.
We had case statements that varied for each letter, and each result would follow along a different math formula and give us different array of y values.
So this letter determines what formula the switch case uses.
The last line of code related to these functions
That do nothing more than change the letter of the formula,
Resets
some variables, and call to
rebuild the array
is on line
1409. After all the mouse down event listeners from lines 1094 to 1108, there are
mouse down advent listeners for the buttons BT and increase speed, BT and decrease speed, BT and increase amplitude, and BT and decrease amplitude. The names of the functions these buttons refer to are increase speed function and
decrease speed function, which, as we recall from
earlier. These functions inside them refer to other standalone functions to change the speed. The increase current amplitude and decrease current
amplitude functions,
also refer to standalone functions to change the amplitude.
on line
1113, there is a mouse children equals false command related to BT and increase trail amount, the button that increases the amount of time to live for the my dogs. After that, there is an add event listener command that ties the function to the button on a mouse click. Below that on lines 1115 and 1116, we have a mouse
children equals false command and an
add event listener command to do the same thing for the button for decreased trail amount. On line 1117, we have the add event listener command for the button that increases our current offset right now by 1.
below that is the line to add an event listener to the button.
For the
button that decreases the same
variable by 1, line 1119 is an add event listener command
for the button that increases the number of keep alives, and below that,
An add event listener command for the button that
decreases the number of keep alives. Line 1121 is an add event listener command that ties a function to a mouse click for the button BTN increase amplitude x5. The function increase current amplitude x5. Line 1122 is an add event listener command that ties a function to a mouse click for the button that decreases current amplitude
amplitude by 5. Function decrease current amplitude
x5. Lines 1123 and
1124 are add event listener commands that tie a function each the button for increasing and decreasing offset amount by 5.
lines
1125 and 1126 are add event listener commands that tie a function
each for the buttons that increase and decrease current speed times 2.
lines
1127 and 1128 are mouse shorten equals false commands so that the buttons for increasing and decreasing the offset amount by 5 are clickable on the entire button.
and not just the text part of it.
Lines 1129 and 1130 are also mouse children false commands for the buttons to increase and decrease amplitude 5-fold. Lines 1131 and 1132 are mouse children false commands for the buttons to increase and decrease speed 2-fold. Lines 1133 through 1146 are add event listener commands for the my dot selection buttons 0 through 13, giving them each the function that changes the my dot selection when they are mouse clicked.
If we have a look at these functions on line 1185, continuing on through
1256, we see that they are mostly the same.
the functions from BTN
Choices 0 through 8 and 10 through 13 are all the same,
and they change the variable called selection of my dot
and when the my dot
selection visibility
function, number 9's button choice function, causes it to push
3 random colors into the array named color array using the dot push command and using math.random property times hex value f. This is done because selection 9 needs at least 3 random
colors to produce bridges.
lines 1147 and 1148 are
add event listener commands for the buttons that
increase and decrease the amount of bridges limited only to selection 9 where
There
there
are bridges and my dots being constructed.
lines 1149 and
50 are add event listener commands
that tie a function to the buttons that turn
Bridge particles on and off. Line 1152 begins
the my dot selection
visibility function. Each time a my dot selection button is clicked,
we would like to see if we should start showing or stop
showing certain extra buttons depending on what the selection is.
some buttons we don't want to be visible if they're not relevant, like the button to increase or decrease the amount of
Bridges when you're displaying a graphicalization of setting other than the one involving
bridges, or the button that
increases or decreases the speed at which the graphic
visualization animation spins.
If you're observing a style that doesn't cause it to spin, there's a good reason to show or hide these buttons.
You can have one function perform the checks and appearance changes and make all
The other functions needing the checks and appearance changes to be done.
Simply run the line of code to call the function.
Our function for doing all the checking, hiding, and revealing is on line
1152.
The first thing it does on line 1155 is
Splice the array color array to its 0 position.
so that it'll empty the variable out and sort of flush out the old colors and get some new ones in next time around.
On line 1156, it performs a test to see if selection of my dot is number 11, 10, or 8, which are any of the 3 selections that has rotation involved. If the selection is any of these 3, we will want to perform visible equals true commands on the buttons for increasing and decreasing rotation speed so that it's shown them. If not, we will want to hide these rotation speed buttons
And also reset the rotation of the graphicalization to an upright state with its y values of this container and the y values of the group inside the container reset to
to the original Y positions. We also perform a test to see if
the selection of my dot is 9, because if it
is we want to reveal the buttons for increasing or decreasing the amount of bridges.
we will also reveal the button for
turning on and off the effect of producing
Particles on the bridges as well. If the variable is not equal
to
to
the number 9, the instructions in the else
coding segment will run. The else instructions
contain code that will make the buttons to increase and decrease bridges and the buttons to turn bridge particles on and off invisible.
because they do not apply it at any graphicalization setting other than
Then 9. On line 1258, there is a function for the button to increase the number of bridges.
It's based upon a mouse click.
This function allows you to add one more bridge by increasing variable how many bridges we have by 1.
Using the ++ operator.
Also at the same time, it pushes a randomly generated color into the color array.
Line 1263.
It does this to accommodate
The need for new colors as the number of bridges is increased.
As it increases by 1, a new number is generated. The function has a limiting statement on line 1260 so that if you have 20 bridges and you try to click this button again, nothing will happen.
Because there is no code for any number of bridges greater than or equal to 20. On line 1266 is the function to decrease bridges.
With the limiter statement basically saying if how many bridges
We have is greater than 2.
Execute the following code.
It's going to make sure you cannot
decrease the amount of bridges past 2.
This makes it so you can't
Run the programming by trying to remove the 2 base bridges.
form the first and end posts. Aside from the limitation, the code within the brackets asks to remove 1 from the variable how many bridges we have
Using the double minus sign, and we use the pop function on the color array line 1271.
The pop function is going to take the last entry in the array and shave it off.
The last color in the array would be deleted and the second to last color will now become the last color. It's a simple command for removing elements off the end of an array. The other code we used earlier to edit
The contents of an array was splice open parentheses 0 close parentheses.
and it slices the tail off to where
0 elements remain effectively empty.
The contents. Line
1275 contains function btn on bridge particles function.
One line of code to edit the contents of the Boolean
Variable bridge particles on to be true.
on line 1279 there to edit the variable to turn it false.
This function btn off bridge particles function.
On line 1283 is timer reset function, which stops the timer, sets the delay to 25
milliseconds for every tick
and restarts the timer. On line 1532, we have bar ratio of how far from left edge you click to the width of clip being defined.
and below it on line 1533 we have the similar variable ratio of how far from top edge
You click to the height of clip.
Those variables are
Essential for centering the graphic after clicking on a location on the video and expecting the program to zoom in on that spot of the screen. On lines 1534 through 1537, we have variables point x where was, point x where will be,
point y where was.
and point y where will be being introduced.
After that on lines 1538 and
1539,
We have variables mouse x change
and mouse y change being declared, which are the final 2 variables needed when
calculating position after upsizing.
on line 1540
the bit of code
Zoom nestor dot add event listener open parentheses mouse event dot mouse down zoom nestor func
makes it so that anywhere you click on the animation, it zooms into that spot.
on the animation by calling upon zoom nestor func.
The program pinpoints exactly where you clicked and
blows the magnification up at that
spot.
Now until code puts sc inside
Inside its object container. SC is just a movie clip sitting on stage
in no container at all. Hence there is no handle to manipulate.
manipulated.
in any way.
All of our frames are just spread out in a sequence on the main stage of the flash file.
And in this position, neither zooming
Nor moving exists for us.
In order for us to stretch, zoom, rotate, and use
Other lines of code we intended for it, we have to put
sc the entire sequence of frames we uploaded
in the prepared object
container zoom nestor.supernester.nestor.
The add child command
command does this. We need to copy down the original x and
and y values that the original clip sits at for referencing purposes. The way we do this
is by creating two variables called
default x and default y
on lines 1542 and 1543 and assigning them the values of the source clips x and y before
doing anything to it. It's going to be sitting somewhere centered in the
screen where we like it because that's where it's centered when we are uploading the frames beforehand.
Line 1544 is where Zoom Nestor Funk begins, which was called in 1940.
It happens whenever we click down on any spot somewhere in the animation. The first instruction on 1547
takes the variable point x where it was and makes it equal mouse
x minus
ZoomNestor.x. It's like taking your current mouse x
coordinate and finding the difference between it and the left edge of the object container
containing the movie clip.
The next line does the same thing with the y, so it's finding the difference between your mouse's y coordinate and the top edge of the container containing the movie clip. Next, it defines variable
ratio how far from left edge of clip
to the width of clip by taking the variable
we just defined, point x where it was,
and dividing it by the width of the object container containing the movie clip. Similarly, after that, it finds the answer to the variable
ratio of how far from top edge
you click to the height of the clip
by calculating
point y where it was and dividing it by ZoomNestor.height. This calculates a ratio in the form of a decimal of how much from left to right or how much from up to down from the edge of the screen our mouse click took place. It is the first element needed in an equation that will simulate a magnification effect at the correct spot in x and y coordinates. Line 1554
increases the x scale and y scale of
ZoomNestor,
the first part of the job, which is
changing the size. Still not done yet.
Finding the x and y points of where this new magnified version
of the clip
calls for you to have to find out how much
recentering needs to be done.
To find that out, we use two variables, point x where it will be and
point y where it will be.
On lines 1557 and 1558.
These are calculated by taking the ratio of how far from
left edge you click to the width of clip and multiplying it by the width of the display object
container holding the clip and taking the ratio of how far from top edge you click to the height of the clip
and multiplying it by the height of the display object container holding the clip. Then we calculate the amount of horizontal
and vertical change on lines 1561 and 1562. Mouse x change is found by subtracting the point x where was minus the point x where will be, and mouse y change is found by subtracting the point y where was minus the point y where will be. Finally, we apply those changes by using the plus equals operator
on the dot x coordinate
and dot y coordinate of our video container ZoomNestor on lines 1563 and 1564. Line 1565
is a line of code
that resets the scale to 1 once you have already magnified by 4.25 times.
This is the end of the function ZoomNestor func. Line 1568 is a line of code that is added to the stage so that anytime a key is pressed, a function will run. It's added to the stage because that's where you would want to add any type of listener that was meant to catch keyboard inputs.
The listener says that if
Any type of key press takes place, capture the details about the keyboard event and run the function check key pressed.
Let's take a look
at lines 1586 through 1632 and function check key pressed. A function that serves as a general throw-all, do-all, and answers back to what the user has pressed. The way it works is, when a key is pressed, it's captured using this thing called an event listener, whose job is to be set up beforehand to sit and listen while taking up a very tiny amount of CPU load. An event listener can be set up to listen for when a key is
released as well. When the key gets pressed,
the character letter pressed gets captured in this part called the event parameter in the form of an integer called its key code,
along with a bunch of things that also get noted and stored, like whether
Control Alt or Shift was held as well. For example,
at the time of the press, the key code is then compared to a whole list of cases
whose instructions can then run independent functions that alter the speed,
offset, amplitude, number to increment x phase by,
or pulsation amount.
I myself particularly had to look online at this big old chart to find out what
key codes were the ones I needed for comparison.
On line 1588, the code asks if the source keystroke was key code 32.
This is the key code for the spacebar, and on this very line of code, it makes a little
moving clip of a hand-drawn spacebar disappear.
Next on line 1590,
the lines of code here instruct the program to add 1 to the value of the selection of my dot.
Why? Because we are using spacebar as the button to cycle through a selection of my dots. If pressing spacebar
causes selection of
my dot to go past the number 13,
we want to instruct to set it back to 0 again. It's important to make checks to show or hide the
buttons for increasing and decreasing rotation
speed, for increasing and decreasing number bridges, and for turning on and off bridge portables. So that's why there's a little instruction there to run the my dot selection disability function after cycling through the selection.
If the key code is 109,
stated on line 1595,
it will call decrease trail amount standalone
function, a function that decreases the amount of trailing pixels
by 1.
The opposite is for key code 107, which will increase the trailing pixel amount by 1.
Pressing key code 188, which translates to comma, will deduct 1 from variable R offset right now. A variable related to how soon
or late in our movie clip, the loop
we are running currently resides.
Key code 190, the period
Does the opposite, it increases the offset, causing us to watch later frames if pressed. Key code 82
is 4R
and runs function timer decrease delay
and reduces the time in milliseconds
between our ticks of 4R main.
program to run main timer function.
Pressing key code
84 for S runs the function to increase the delay.
or timing between ticks of running main timer function. Key code 68
For character D,
calls a function to
Toggle the visibility of everything
except the movie clip inside graphicalization. That includes large descriptive buttons, demonstrational
text, and variables
showing in the background.
Pressing key code 37, the left arrow shifts the container supernester to the left from line 1603 through 1605.
The key code 39, the right arrow, 38, the up arrow,
and the 40, the down arrow.
all do the same thing, shifting supernester in the direction respective to their arrows. Pressing key code 74J calls increase speed function standalone related to the number to increment
XY. It'll speed the rate at which we proceed through the curvatures of the
graph. Pressing key code 72H calls the decrease
speed function standalone, which does the opposite, slowing the rate at which
X proceeds. Line 1608,
Referencing key code 78 or N lowers the amplitude coefficient. Y
ranges are going to be closer to one another.
curves are going to be less prominent. It should be reducible
until it is the smallest it should go.
a value of 0.02. This would prevent too extreme
of values and make it impossible for you to crash the program by trying to reduce the amplitude to
too many decimal points close to zero. Pressing key code 77, the code for letter M, increases the
amplitude by calling the increase current amplitude standalone function on line 988. Amplifying this would multiply all values, and the difference would be the range of frames being larger. It will be more jerky, spinning wider across more
Frames of time. The key code for K
is 75.
And if you press K, it gives the display object container zoomnester.supernester.nester.
A slight shift in rotation clockwise, a value of 5. Recall that
Nester is a container designed to let us rotate it.
Supernester is a container designed to let us stretch. By having a different container to rotate and stretch,
You can allow yourself to rotate with the intention of getting things first into alignments that you want to stretch, and then stretching after those alignments being made.
Key code 76, the letter L, does the opposite.
causes a shift in rotation counterclockwise 5 units. Line 1612 says that
Key code 79, otherwise the letter O, will take the scale X value of supernester
and decrease it by 0.05, while taking the scale Y value and increasing it by 0.05. This is making the image stretch narrower and thinner. It's worth mentioning 3 things. First, there is a
Comparison of the value of zoomnester.supernester's scale X
value to
the number 0.19, limiting you from squishing it past the
narrowness of 0.19. Next, it increases the scale of height
and decreases the scale in width as mentioned. Thirdly, it adds to its X coordinate 0.025
times SC.width. And what that is going to do is make it move in a way that recenters itself left to right after changing. Likewise, at line 1619, it subtracts to its Y value 0.025 times the source clip height,
so that it aligns itself vertically after changing.
Line 1622
through 1629 do the reverse if you press P for key code
80. It tests the Y scale to
See if it's at least greater than 0.19.
Why? Because we're going to shrink it and want to know if it's at least wide enough to be shrunk one more time. Therefore, if it passes the test, the scale
X are being added 0.05. The scale Y
are being subtracted 0.05. The X and Y scale change result in the image float.
like a pancake.
Recentering is done horizontally and vertically by adjusting the .x and .y properties using the same math we did
as before with the opposite operators.
On line 1569, there is an add event listener command that ties a mouse click listener to the button
BTN reset button to call for the function
reset function to run. On line 1570,
There is a mouse children false command because of the fact that there is a text box inside the button.
on line 1572,
function reset func is found. Reset func is a function that will restore
restore the view.
It does so by resetting the source clip nester, supernester, and zoomnester properties altogether. The source clip's X and Y properties, which are the ones that
The user
can manipulate using arrow presses.
are restored on lines 1575 and 1576. On line
1574, the surface most
container nester, in which the source clip directly sits and handles rotation
only has its
rotation property restored back to 0, so the image will be at its normal stance
upright. On line 1577 and 1578, scale edits on the second most surface container supernester
associated with stretching
are restored to default. Below that, on lines 1579 and 1580, the translation edits
that must take place when stretching vertically or horizontally
to keep them centered. Also on the supernester character layer are restored to default. Below that on lines 1581 and 1582,
the scale X and
scale Y properties that are changed in the means of blowing up the size on the third most
surface container zoom master
are restored to a default value of 1. Lastly, on lines 1582 and 1583, the X and Y translations that are made in an effort to keep the image centered when you zoom in on it are reversed back to 0.
There's no more code in reset function, and there is not much to talk about left
except
the programs at the very end of the main stage code. On line
1634, we have function random 2. Function
random 2 is a very basic line of code that
comes from a reputable source on the internet. It's called random 2 to plainly represent that it outputs a random number 1 being given 2, of which are going to be its minimum and maximum. What's returned is a number,
and you can see the word number right after the colon in the function header.
It's
unlike all our previous functions that do not return a result in the form of any code.
The opening bracket which starts the code and the end bracket which closes the code and the code itself are all on the same line. The code says return math.round open parentheses math.random open close parentheses times open parentheses max minus min
close parentheses plus min close parentheses.
It's going to generate a single point number between 0 and 1 that starts out as our range
unapplied.
We have to multiply the range unapplied times the range, the max minus min, to get our applied range,
which is not an amount to be satisfied
with yet because it's still not in the right bounds.
Add the min value
to the applied range that's not in the right bounds
yet to get a number to be satisfied with that's in the right bounds. That number now still isn't useful yet
because it hasn't been routed to a whole number, so round that result
to the nearest whole number to get an official random whole number within the bounds. Line 1644 defines a function called the showDisplayList function.
The function is only useful for programmers to allow them to access the
display list, which is
for application designing purposes only.
The use for it is to display what is normally invisible to an
Adobe Flash/Adobe Animate user.
The display list. The display list for some reason just can't be shown as simply, but it's
there and ever changing. It's the list of every single object currently being displayed in the scene.
The way you get the display list to show up in any form is in a text list, and you have to first create a function to utilize a bunch of trace commands in a clever way in order to get that list. To pull it off, we use the trace command in a for loop, and we do it in a dynamic way, whereby we use object.numChildren as the
comparison value, so that we can not have to know how many there are and still do it. To find out if a child exists, you first have to reference it by position, and if you don't
know how many objects there are at any single moment in your scene,
that's going to be a problem usually.
They're all called children,
essentially, because they're all linked to another object in such a way that
when that object is dragged or pulled, that object moves the object in discussion and not the other way around.
The parent of an object is
always the container it is directly contained in. Likewise, a child of a
container is always directly
contained within it.
Object-oriented programming is a way to let you
create endless objects or variables to infinite
repetitions by using a basis
of copying to some extent from another object and utilizing
similarities while clarifying the differences.
Doing this saves you the time of building every single object type from scratch.
It's a whole conversation on its own.
But the two main premises of object-oriented
programming are the relationship between a parent
and child
and the relationship between a class and an instance.
A parent is something that has
a child
anchored to it in purely a form of metaphorical containment. That means if an object has another object on the screen centered inside of it that doesn't
describe it as a child of the other, you have to set children using the menu. Once you set a child to a parent, it's pinned to it
at its location
relative to the other and moves when the other moves.
A class is a
predefined set of
properties about a make-believe object, and instances are singular takes about those predefined classes. An example is, my baseball is a baseball,
which is a sports ball, which is a ball,
which is a spherical object,
which is an object,
which is a thing in this world,
where we have an instance at the head of the sentence, several subclasses in the middle of the sentence, and the root
class at the end.
If my program were about clicking baseballs,
then the baseball which came on my screen at 12:03 p.m.
that I clicked within 150 milliseconds of it being on screen, that we were keeping track of its secret hidden dollar amount is an instance. That single baseball is the instance, and the class properties would include hidden dollar amount, time clicked,
how long it took me to click it,
and probably its index number would be important too. If I needed a million dominoes to display on the
screen on and on,
the domino is the class, and even the amount of space that should be in front and behind it can be a part of the class too. But the intention is just to build something so that
you can repeat it
over and over again. If I have a game about a main character human talking amongst other humans, and I needed to log what emotions they leave other characters in as they speak to them,
I might want to have
a human's
class. If I want to keep track of where they
left off in the conversation with each person,
but I didn't know how many
of these people I was going to need,
I would make humans a class just so I could keep track of all these things and possibly
expand on them later. As the game would plan and develop,
adding more and more humans would be easier. You would choose to edit out single variables for each different one, like first encountered things they say,
how fast their speech rate is,
or whether you can skip their dialogue or not.
What could also be a property of a class
is their X, Y, and Z position on the map of your game. It's all about how you're building this imaginary information that you wish to store in a way that will
allow you to reuse what
you've already defined. You
create more and more copies of things while using
With less programming space.
We use MyDots as objects that have properties and methods internally that cause them to move and disappear. We use them in sequence one by one after another to simulate the essence of flow on the timeline, to demonstrate how forward or backward in time we are on a linear graph.
We had an instance created at every tick of the timer
And anchored the creation to a process we could get to occur periodically.
and control its frequency.
Every MyDot had a time-telling variable,
One we can make greater, and its effect would be to
stay alive a little longer,
which would cause the little
tail
tail
to go a little longer. Every MyDot had a way of proceeding, whether it was moving in the direction of the mouse,
Moving in the direction you are traveling currently, or moving upways or downways. Its MyDot once created is parented by the container
Buttons container dot rot container group 1. When we use
the add child command. The MyDot becomes a
child of group 1, a child of rot container.
rot container being already a child of buttons container, which itself is a child to the main stage.
At the end of the day, it's going to have an amount of instances of MyDots in it, and we're not going
To know how many there are, or will we ever
Really care. That's the whole point, that we can have all these bouncing, crazy amounts of objects working the way they work
without us not even knowing or
being limited
by needing to know how many there are ever going to be. When I do want to know how many children
are in the display
playlist. It's to know how many there are
to get a number for
arranging,
for ordering
purposes, such as to order them manually from front to back. I could use the program show display list at any time.
in the pre-production mode to have
trace commands tell me what objects exist while the application is running. Line 1644 is the header and defines the function, and it requires you to pass into it a display.
Display object container. Each time
you use the function
When you want to know what's on the display list
of the
the
whole
entire scene, the display object
container is
the stage, so you would type show display list,
open parentheses
stage, close parentheses. Line
1646 uses a for
command, and it says, for the case that variable I is going to be an integer,
it's going to be equal 0 to begin with and will carry on repeating as long as it satisfies the condition.
less than object.num children. So it's going to run, and I is going to increase by 1 every time it's done.
And once I has become
a number that is no longer smaller than the display object container's amount of children, the program stops repeating. The trace command will,
on line 1648, present us to a combination of the string of the
Blank quotation marks plus object.getChild and I.name. Now, you want to combine a blank set of
quotations plus the value of object.getChild of I.name, because you cannot just spit out the object.getChild at I's name.
You have to first mash it together with a set of quotation marks.
And then what exactly is getChild at of I? The getChild at command is a way to
Grab an object, whatever it is, wherever it is, in order to change it or do something with it. Once you have an object highlighted, you can ask the program to spit out its name in a trace command by using its .name property. The reason we have an I in lowercase is because we need a position number or an index number
in pairing with the getChild at command, because when you intend to read a child in a list of children
from a parent, you need to consider that it is a list, and with all lists and asking about a list,
need to include what position.
Using I, this lets us use a positioning number that can be borrowed straight from the for loop itself, which will always make sure to run every number and won't skip any digits.
When it runs for the first time,
It'll read the 0 position child of the display object container we passed through the very first test. The second passing of the for loop, when it indexes at 1, will grab the second child, so that will successfully present that child's name.
it will go all the way until the stage has no more children left to identify.
It is important to ask if the child being grabbed is a display object container in the code,
Because you want to run this function
on any display object container you come across.
in running this program.
as well, so that you cover the children of children and completely get everything. While the child is highlighted, it is put into question whether it is some standard object or it is a display object container. That happens on 1650 and 1651. It asks
If object.getChild out of I is, and the word is happens to be purple because it is a special command.
It allows you to compare variable names and variable types. If that
child we've highlighted is a
display object container, then run this program again.
But only on this child. We do then by calling the function again from within the function itself, using show display list from
Within the function show display list, and that's completely okay, and it will perpetuate forward for every child and their children.
each time passing through the function a new object from the stage, displaying their names line by line.
In the trace output window,
Once that's done, nothing else happens.
we've now reached the very
End of our code, and we have now considered
all things it takes to get this program to run.
We've covered the ways the program calculates the
Graphicalization,
the way the program comes up with the graphs,
and how
keystrokes
Manipulate the program.
We've covered a game about a main character human talking amongst other humans, and I needed to log what emotions they leave other characters in as they speak to them.
I might want to have a
Humans class. If I want to keep track of where they
Left off in the conversation with each person,
but he didn't know how many
these people I was going to need,
I would make humans a class just so I could keep track of all these